In our last video, we worked on graphing logarithmic functions based on the fact that exponential functions are their inverse. And we're going to talk a little bit more about how to graph these log functions and then go into more detail about finding their domains. So I wanted to take another look at number 29. So remember we graphed g of x equals log base 2 of x plus 1. And we started with our function, our exponential function. Right, we started with our exponential function, y equals base 2 raised to the power x. We know that its inverse function would be y equals log base 2 of x. And then we used a transformation to shift this. Into y equals log base 2 of x plus 1. So we started with our xy table from our exponential function. We switched our x and y. We started with this, go back here. We started with this xy table in purple up at the top for our exponential function. We switched to this blue xy table, which is copied down here. So this is for our log function. And then we shifted it, in this case, shifted it to the left one to get our final xy table graphing this function. So that's a little long-winded. So you're probably thinking like, oh my gosh, this is driving me crazy. Can't I use my calculator? And the answer is yes, but. So remember, to graph number 29, you can't use the log button. You can't use the log button. We can try. Let's go ahead and try it. Why not? Y equals log, and then in parentheses, x plus 1. We'll graph it. And it kind of looks like our function, but let's go ahead and use the trace key. So if I type in -1/2, which is -0.5, that gives me y equals -0.3, but I should be getting a -1 there, right? I can see that the function goes through 0, 0, so that's a match, but this point doesn't match up. If I hit x equals 1 and hit enter, I get y equals 0.3, that should be a 1, 1. If I hit y equals 3, I should be getting y equals 2, but I'm getting y equals 0.6. That's because this log button is for the common log with base 10. Our function has a base 2, right? We also can't use that natural log button to graph this because that would be a base e. So we don't have a log base 2 button right here in our calculator, but there is a way to get to it if you have a nice new fancy calculator. So if you go into y equals, and you hit the math button, so hit math, that's where a lot of goodies are hidden. And then you scroll all the way down. My menu probably looks a little different than yours, so you'll probably have more options. But if you scroll all the way down, sometimes it's faster to hit the up arrow to go all the way down to the bottom of your list. It's pretty close to the bottom. And you have this log base function. So log base function. So if you have this in your calculator, congratulations. Graphing these log functions is way easier for you. If you don't have it, sorry about your luck. But you can always use this method that we used before, basing it off of the exponential function and using the inverse properties. So if you have this log base function, that's super, hit enter. Remember, we are already in y equals. So now we have log, and then you can see a little cursor where the subscript is going to go. And I'm going to type my 2, log base 2, and then scroll over in parentheses and type x plus 1. Now let's take a look at our graph. All right, I'll hit the trace key again. Trace, remember that's how we can type in x values to spit out y values. So let's test this table again. So let's see if these guys work. I'll erase these x's and check marks. All right, so let's see. I'm just picking out a color. We'll do blue. All right, so using our trace function, first let's type -1/2, -0.5, and I get my -1, so we've got a match. Type 0, get my 0, there's a match. 1 gives me y equals 1. Type x equals 3, hit enter, and I've got y equals 2. So you can graph these using your calculator, but you need to use that log base and dictate what the base is. You can only use that log button if you have a base 10, which you might have that example, but just be really careful about using that. All right, and actually before we scroll down to the next page, which is all about finding the domain, I just want to talk a little bit about this domain that we already calculated. So we can look at this function and tell that the domain goes from -1 to positive infinity, but how could we find that more algebraically, just solving for it? So whenever we're taking the log of something, remember we have the log, there's base b, and then we're taking the log of something and we call that the argument, right? So the log base b of some argument, the something that we're taking the log of. The argument in number 29 is x plus 1. And that argument always has to be positive. It can't even be 0. It always has to be greater than 0. Not 0, nothing negative. So whatever the argument is, the argument has to be strictly greater than 0 for any log function. And we can test this. I'm going to hit second and quit. So we can test this just with our common log button. So common log of 7 is 0.84. Common log of 1 is 0. Super. Log of 0. Oops, sorry. Let me clear that out. Didn't mean to do the double 0. Log of 0. You'll probably see a different error message, but you'll see some sort of error message on your calculator if you type log of 0. If we type log of -1, another error message, maybe a different one, but you'll get an error message on your calculator. And this is true no matter which log base we pick. So even if I do log base 4 of -1, I get an error message, okay? Natural log of -1, I get an error message. Any logarithm, the argument has to be greater than 0, okay? So in this case, the argument for number 29 is x plus 1. So we want to solve x plus 1 is greater than 0. And then, of course, we could just subtract 1 from both sides, which gives us x is greater than -1. And in interval notation, that's -1 to positive infinity with rounded parentheses. So whenever you're asked to find the domain of a logarithmic function, take whatever you're taking the log of, which is the argument, and set it greater than 0. So for number 30, find the domain of f of x equals log of 5x minus 1. So whatever you're taking the log of, you're going to take that 5x minus 1 greater than 0 and solve that inequality. So I'll add 1 to both sides, which gives me 5x, greater than 1, and divide both sides by 5. This gives me x greater than 1/5. Convert that into interval notation. So the domain is from 1/5 up to infinity. All right, for number 31, find the domain of f of x equals natural log of 7 minus x. We're taking the log of 7 minus x, that's the argument. So we're going to solve 7 minus x greater than 0. So you can do this a few ways. Probably most of you guys would subtract 7 from both sides. Then you have -x greater than -7. You'll divide both sides by -1, divide by -1, which then flips your inequality, gives you x less than -7 divided by -1 is +7. So in interval notation, -infinity up to 7, rounded parentheses. Okay, and we can check either of these graphically. So for example, for number 31, we have the ln key. So go to y equals, I'll clear this out, natural log of 7 minus x, hit graph. And we can see visually that our graph is kind of petering out at this x equals 7 vertical asymptote. So if we use the trace function, if x equals 5, there's 0.69. If x equals 6, we end up at the intercept 6, 0. X equals 6.7, -1.2, 6.9. So I'm getting closer and closer, or I'm getting, more and more negative, 6.9999. So you can see the y value is becoming more and more and more negative, and that's our asymptotic behavior at our vertical asymptote, x equals 7 in this case. All right, now that brings us down to number 32, which is a little bit of a doozy. Number 32 says find the domain of the logarithmic function and we're given h of x equals natural log of x squared minus x minus 30. So we need to take this argument, x squared minus x minus 30, and set it greater than 0 and solve that inequality. Now, in order to do this, it's helpful to get this in factored form. So factoring the polynomial, we have x minus 6 times x plus 5 is greater than 0. And remember, when we have these quadratic inequalities that we're solving, in the past sections, we use these test intervals. So what I'm going to do is find boundary values. And that comes from setting each of these factors equal to 0. So if I set x minus 6 equal to 0, I get x equals positive 6. Setting x plus 5 equal to 0, I get x equals negative 5. And these are just my boundaries on my graph. So I'm going to draw little dashed lines here at x equals negative 5 and at x equals positive 6. So this creates 3 intervals on my graph. And what I want to do is I'm trying to solve this inequality. So I want to see when I multiply one factor by another factor, I should get a positive result. Because we're looking for greater than 0, I want positive results, right? If it were less than 0, I'd be looking for negative results. So what I'm going to do is identify a few test values, which are just any value in all 3 of these intervals. So for example, in the far left, maybe I'll use negative 8. Sounds good to me. So using these 2 factors, x minus 6 becomes negative 8 minus 6. X plus 5 is negative 8 plus 5. And at this point, I can convert these into negative 14 times negative 3, which is positive 42. But honestly, all I care about is that this is a negative number and this is a negative number. And 2 negative numbers multiply to a positive number. So this is going to be true for any values. If you guys had picked negative 11 or negative 6 or negative 7, any value in this interval, if you plug it in for x, it's going to produce a positive result there. So I'm putting a big plus sign in that interval. In the middle interval, 0 is always pretty easy to work with. So 0 minus 6 times 0 plus 5. 0 minus 6 gives me negative 6, but I just care about the negative sign. 0 plus 5 is positive 5, but I just care about the positive. Negative times positive multiplies to something negative. So I'm putting a big old negative sign in the middle. And then over here to the right, pick your favorite number. Let's be zany and pick 11. So we've got 11 minus 6 times 11 plus 5. 11 minus 6 would be 5, but it's a positive 5, which is all I care about. 11 plus 5 is positive 16, but all I care about is that it's positive. 2 positives multiply to a positive value. Okay, so how do we express our final answer? We've got positive, negative, positive. We're looking for our positive results. So I want to represent this interval and this interval in my domain. So the far left interval is negative infinity up to negative 5, rounded parenthesis. Remember, we have that strict greater than inequality. The far right interval goes from 6 with the rounded parenthesis up to positive infinity. And I can connect these guys together with that union symbol. And in your homework system, it might just ask for a comma or the word or something like that. But at any rate, our domain is the region from negative infinity to negative 5, and also the region from 6 to infinity.